I'm assuming you have some knowledge on the electron transport chain that's happening in the light dependent reaction in the photosynthesis. But if you don't, I think here is like a basic rundown. This is a diagram. So basically, now I'm only going to talk about the non-cyclic photophosphorylation, which goes from here to here in a zigzag motion, or a Z scheme. I think that's what they call it. And now I'm gonna assume that you already know what this is, and I'm going to explain in a bit more detail how these electrons, how they replace themselves and how they are used for the reduction of NADP. It just gets a bit more clear once you actually gets to see like which electrons are being like used for reduction and which ones are replaced. So let's go. So this is gonna be my basic platform here. This is gonna be my photosystem 1. So this entire page is a photosystem 1. This page is photosystem 2. Wait, sorry, it's all the way around. Sorry, my bad. I always get this wrong. So ignore what I said just now. This is the photosystem 2. And imagine here you got like a chain of electron transport molecules or carrier molecules, we say. And then this page is the photosystem 1. And this page we have here, this will be the place where the NADP is, and this is where the NADP gets actually reduced into NADPH. Okay, so let's go. So we know that the photosystem 2, we know that photosystem 2 and photosystem 1 at the reaction centers, they each have 1 electron per reaction. So this is their electrons presented by these 2 pens. And right now they're unexcited. They're just sitting there in the reaction center, which is inside the photosystem. And now let's just say there's like a sunlight that's shining through, like on top of the plant. This sunlight, so you know that light energy, or what we say as photons, they can actually excite like the accessory pigments that are around the reaction center, and eventually the energy gets passed down to the reaction center, and these 2 electrons, they'll become excited, so their energy level will increase. By the way, this line, you can imagine that it represents the energy level. So the energy level increases. And now, the electrons are gonna get passed to like the transport carrier, or should I say the electron carrier? Anyways, this is called electron carrier. It's gonna get passed on, both of these electrons, this one photosystem 2, this one photosystem 1. They're gonna get passed down to the carrier molecule that is right next to them. So if you remember from the electron transport chain of respiration, aerobic respiration, every time I move this electron to a carrier molecule and to the next, the energy level actually decreases. So just keep in mind the energy level decreases as it passes down to the next carrier molecule to the next. Okay, so now you might have noticed something. So now my electron that's originally from photosystem 2 has actually moved to photosystem 1, where actually now it gets excited back again, and it will actually happen again. But so now you just keep this in mind. So now the the electron, the excited electron, after like releasing energy on the way, it actually gets into photosystem 1. Later on, we'll get re-excited again, but that's not happening now. So what happens? So now the original molecule that was from photosystem 1 is actually now like out of the photosystem 1, and now they're here, right here. Just now I said this is where you have the this is where the reduction of NADP takes place. So imagine here we have like one NADP molecule. So if you remember the equation, one NADP molecule requires 2 hydrogen ions and 2 electrons to be reduced into an NADPH. So now I already have an electron here. I just need another electron I need another electron and 2 hydrogen ions in order to reduce my NADP into NADPH. But now I only have 1 electron, so that's a big problem, right? I need another one. I need 2 H pluses. So now what will happen is, here we have a reaction. So on this table we have another reaction. This is called the photolysis of water, and the photolysis of water is basically where water is getting broken down into 2 hydrogen ions, 2 electrons, and half of a oxygen molecule. But ignore the oxygen because that's a waste gas. We're focusing on those 2 things being produced. And remember, the photolysis of water has to be catalyzed by the enzyme called oxygen evolving complex. So yeah, imagine you have a water here, but now it breaks down into, this is my 2 hydrogen ions, and these are my 2 electrons. So I'll talk about the electrons first. So one of the electrons, if you check the entire system, right here, you'd realize that, hey, I need like another electron for my photosystem 2. Because if I don't have an electron here, how can this? There's nothing for sunlight to excite, right? So in order for this like reaction to continue going this way, I have to replace an electron here. Therefore, one of the electrons from the photolysis of water will replace the missing electron from photosystem 2. So the other electron here produced in the photolysis of water, you might have guessed it, it will go to the reaction for NADP. So now we have 2 electrons. That's all we need. Well, we need another 2 things. That's the 2 hydrogen ions we have here. And since that's also produced during the photolysis of water, I can just add that to the NADP. And now, since I have all my necessary ingredients or reactants, I have produced my NADPH. This is my NADPH. Or reduced NADP. And that's basically the reaction. And if you're not convinced enough, see how I have replaced my electron at the photosystem 2. Now the reaction actually happens again. They get all excited again, and then they get like, as they pass down from the carrier molecules to the next, they release their energy, and then now I need the photolysis of water will happen here. One of the electrons will replace at the photosystem 2, and one of the electrons will join the reaction taking place here, and the 2 hydrogen ions also join here, and this way we can form our NADP into NADPH. So that's basically it.